welcome you for your talk, Professor Haicheng.
Okay. Good afternoon, ladies and gentlemen. I'm glad to be here to give you a talk about nuclear data development related to the thorium uranium first cycle in China. I come from the China Institute of Atomic Energy. Also, my group is China Nuclear Data Center. Here's the outline of my talk. First, I will give a brief introduction of the research background. Then I will talk about the measurement of neutron-induced fission yield, and then talk about the systematic study on the thermal cross-sections. Then the evaluation work and validation work for the nuclear reaction date and decay date, and so on. Then end with a brief introduction of Sender TMSR library. As you all mentioned yesterday and today, is the Fourier cycle, which is regarded as a supplementary of the uranium Fourier cycle, draws a lot of attention. I was told from the users that the top priority requirement of the improving the nuclear date used in the neutronics study for the thorium reactor is first is the general proposed nuclear reaction date for thorium, protactinium, and uranium, and also the decay date for mass in the mass chain 232 and 233 and 234. Also, the fission product yields for the thorium 232 and uranium 233 are very important. To meet the requirement, there are quite limited research activities have been carried on since 2010 in our center, including measurement of the fission product yield for thorium 232 at 14 MeV, and study the systematics of the thermal capture cross-section for actinides, and also evaluation and validation of the nuclear reaction date for uranium 233 and thorium 232. Our work are mainly focused on 12K nuclides, which is colored in this figure. First, measurement of the fission yields. The fission yields for the thorium 232 is measured by the direct gamma spectrum method. Most of the fission product activities were measured by the high purity gamma ray spectrometry. And nearly 70% of the yields were directly measured, and unless those unmeasured product yields were interpolated or extrapolated based on the current evaluations. And the normalization is 200%. The relative uncertainty we got in the experiment is less than 5% for the two fission product peak. Unfortunately, we found that in our comparison between the our experiment data and the current evaluations, we found for some isotopes, for some products, the accuracy of the evaluated date may not as good as we expected. The discrepancy sometimes goes up to 20%. And that's the fission product. Then let's talk about the thermal section. As we now know that the thermal fission and capture cross-section are very important in our thermal reactors. To design thermal reactor, you need very accurate these cross-sections. But in current nuclear data evaluation work, most of the thermal cross-sections are evaluated based on the experimental data, and there's no good theoretical solutions to calculate this kind of cross-section directly. So for thorium and protactinium, there's no good, they are short of experimental data, so it's not very difficult to evaluate this kind of cross-section. And also, there are no good systematics is available for these cross-sections. Here, I should say, there's some work related to the systematic already been done many years ago, but they are unpublished one. So we began our study with assume an experimental formula from the Bohr-Wheeler formula, and we assume that the cross-section in log is linear with this idiom. Instead, it's represented the excitation energy for the compound nucleus. To obtain the systematic, we have to recommend a site of thermal fission cross-section, and also recommend a site of single peak fission barrier for this study. These data are recommended based on Sendo 2.1, Index 7, Gendo, and also on REPO and Atlas of neutron resonance. We found that when we set the parameter C in the formula equal to 3, then the thermal fission cross-section can be illustrated as the formula quite well. Both the odd-even effect of proton and and the shear effect in the neutron dependence are observed. Here is the shear effect of the neutron for each element. And in this graph, you can observe that here is the charge number dependence here. We found that when after we got the parameter A and B for each for each element, then we can calculate the parameter. We can obtain the A and B in a very general way, because for the old Z, the parameter A and B can be illustrated by the linear function of Z, and for even one, parameters can be illustrated by the quadratic probable function of the Z. So which gives us the final formula like this kind. And then by accomplish this work, the thermal fission cross-section becomes predictable by the systematic methods. Where for the thermal capture cross-section, the situation is completely different. There are also no systematic for thermal capture cross-section for actinides. The only work related to this is in the European activation file evaluations. The Mr. Kapetsky use the formula, use this formula, which is used for the 30 it was worked with the 30 keV neutron, but now In EAF 2009, he used this formula also for the thermal capture cross-section, but you can see that the divergence of the data are quite large. We try to decrease the divergence of the data with updated experimental database used in the evaluation, and also with the updated level density parameters of actinides in the formula, and but it's not successful. So there is still no effective ways to calculate the thermal capture cross-section in this. So that's. Let's come to the evaluation works related to the thermal uranium fuel cycle. First is decay data. The nuclear decay data and the structure data are evaluated simultaneously for the mass chain 232 and 234. And we found there's no significant change of the half-life for this for these nuclides. But since there is some new evaluation method and experimental data there, the decay scheme has been updated. Let's come to the fission yield again. This is about this is the evaluation of the neutron field yield for the thorium 232. The accumulated fission yields and the mass distribution were evaluated through the comparison of current evaluation B7, GF 3.1.1, and GENDO 3.3. We mainly focus on the fission product yields, which is interested in the Bernard corrected calculation. For some nuclides, for some of them, like CIAE133, GF is recommended, and for the Semenya 152, INDF is recommended. In these two figures, you can find the difference between the GF and the INDF evaluation for the fission spectrum is quite large. The final evaluation was obtained by a combination of B7 and GF. Also with the yield of Semenya 152 and European 153, and also the yields on the same chain were adjusted. These two are mass distribution for the fission spectrum and for 14 MeV. This is our work about re-evaluation the nuclear reaction data for uranium-233. Before we come to re-evaluate start to re-evaluate the nuclear reaction data for the uranium-233, benchmark work had been done at first, and we found in the uranium-3 metal fast system, the CLV value of K effective is underestimated very seriously by CENDO 3.1, also by GENDO 4.0, but they are better. And we, especially for the beryllium and tungsten reflected benchmarks, we performed we do the sensitivity analysis on this benchmarks, and then find it was mainly caused by the inelastic and elastic cross section. So we revised these cross sections, and also we revised the fission cross section resonance parameters and accurate distributions, and so on. And then we have a better uranium-233 which also the CIAE value can be almost unity when we change the unit to 33, and also we need to replace the date for the beryllium and for the tungsten. So the things comes like this. For 7232, we found this is the CIAE value for the KPR experiment with the episomal and the faster spectrum are various over predicted by Sendo 3.1, which was caused by the N-gamma cross-section in the range 4 kV to 1 MeV. This region was in the unresolved resonance in the unresolved resonance region. So we re-evaluated this cross-section based on the G artist's work, and there's a little different here. For INDEF7, they fit this cross-section with all this experimental data, but we only choose one here. Especially to keep this peak here, we can make the CIAE value a little better than B7. For other nucleus, we also for other thorium, protactinium, and uranium also made a comparison and recommended the date, the best date as we can. There's quite limited experimental data for these isotopes. So better evaluate our criteria to select to recommend this date is mainly is to see whether the theoretical calculation is reasonable, or if there is an experiment available, we will also to say if the evaluation is good, have good agreement with the experimental date. Our recommendations are listed in following table. Protecting and 231 and 233 from INDEF7, which is evaluated, I think, in the CIAE CRP, and uranium also comes from INDEF7. All the thorium isotopes here comes from we recommended Gendo 4.1 and also protectin 232. I list some some pages here. There are some figures for these isotopes for the fusion cross section of 7230 and 229. This result comes from evaluation comes from the GF. It's quite strange, and also the inelastic cross section here is strange. So GF is not so good, and Gendo is have reasonable results. And for protactinium 231 fusion cross section, GF is look like this. I don't know why. And also the double differential cross section for at 14 MeV induced by 14 MeV neutron. The direct reaction component is missing in the GF's evaluation, and for B7 and for Gendo 4 is better. As I just said, before our evaluation, we performed the benchmark testing for uranium and thorium evaluations before 2010. There are total 159 cases for uranium-233 and 55 cases for thorium-232 were selected from the SSBP handbook. This benchmark contains the fast, intermediate, and also the thermospectrum systems. Here's the result for the uranium-233. Uranium-33, and for fast spectrum, I already talked about it. For the thermal solution system, and also for the epithermal solution system, we found that the silver E value were seriously underestimated, which is dependent on the spectrum index. For all these libraries, the results are not very good. We look into the resonance parameter and found that almost all the resolved resonance parameters comes from I forgot gender work maybe. So they are exactly the same. So our libraries gives quite bad results here, which is still need to be improved. For the thorium cases, we find for KBR and THR benchmarks, CIAE values are good for the THR, but for KBR values, overestimation is still there, even with new evaluated thorium cases. It's still maybe it's about 500 PCM overestimation for the epithermal and for the epithermal and for fast reactors. And for the thermal system, we tested the thorium data with benchmark SB and also the HTC, which is the high enriched uranium compound thermal systems. Which give me surprise is that for this site of experiment, we found that the CIAE value can be overpredicted, also depending on the spectrum. For EAF values less than 0.22, the CIAE value is inside the uncertainty of the experimental date. But when spectrums getting harder, overestimation is found. So this benchmark result shows that the resolved resonance cross-section for thorium-232 N-gamma maybe not still a little low. I don't know why this is not the final version of my presentation, I think. And okay, let's come to the validation work for the new standard evaluations. We can find with revised thorium-232, uranium-3 and hydrogen-1. The CIAE value for the the uranium compound thermal system. It works very well, and also for the water reflected uranium solution systems. So as a fruit of our work, a hybrid library was recommended based on CIAE 3.1 and other libraries. There's total 400 nuclei in this library. I come to my summary. To improve the nuclear data related to the thorium-uranium fuel cycle, some nuclear data have been measured or reevaluated. Failure yields were measured with uncertainty less than 5% around the 2 peak of the mass distribution. Systematic formula for the thermal fission cross-section was obtained, and the nuclear decay data and structure data were reevaluated, and the data scheme were updated. The fission productive yields for the CIAE was recommended based on the combination of B7 and GF 3.1.1. Nuclear reaction data for the thorium-2 and the uranium-3 were revised and improved based on the feedbacks from the benchmark testing. And the results show that the resonance parameter needs to be improved. There are still some research works need to be done to improve the fission yields for thorium-2 and uranium-3, and establish a reliable theoretical or statistical ways to calculate the thermal capture cross-section, and to continue to improve the neutron reaction data for uranium and thorium isotopes. There are so many others that I cannot fully list it here. There's a question before you ask me a question. Are the current nuclear libraries are good enough for the engineers to design a thorium reactor, even for get a license? Okay, that's my talk. Thank you for your attention.
Okay, thank you, Dr. Wu. So the talk is open for question. Dominique?
I'm very sorry to take the mic again, but you will understand why. It was exactly the topic of my PhD 40 years ago on thorium cross-section, so I cannot avoid question on this. Could you, first a clarification, could you just project again the slide number 17, bottom left, where you plot the cross-section, capture cross-section of thorium? 40 years ago, the value was 7.4 barns, and I am discovering it's less than 1 barn here. So maybe there is something wrong. I mean, for thermal range at 0.1.
This is not for thermal.
This is 4 keV.
This is 4 keV to 1 MeV. This is unresolved resonance
region. But even in the thermal range, oh, sorry, it's MeV. Oh, yeah, okay. Okay, so maybe, okay, thank you very much, because I'm reassured that the thermal cross-section has not changed. My second question is about the resonance integral. At that time, you were not born. I evaluated the resonance integral of thorium, and I remember it was 83 barns, plus or minus 2. Does this, I will sleep well this night if you tell me that this is the same value today, 40 years later, or maybe you don't know the value. Okay, the resonance integral is no.
I didn't. But, okay. I didn't evaluate the resonance.
The last point important is about the fast neutron capture cross-section of thorium. At that time, it was 20% higher than the value, you know, compared to integral. You say, Ojoru, it's today that it's lower the predicting. So what is your reason for that? You said that thorium cross-section is lower than... you said this thing somewhere.
The summary.
Yeah. Sorry to hear you.
This figure.
In other words, a very quick answer. Yeah, region is too low. You say thorium in fast range region is too low, and I found at that time it was too high. But what is the uncertainty today on the thorium cross section? Clearly in percent. At that time it was plus or minus 20%. It was improved.
This conclusion is for the Sendel evaluation, the old Sendel evaluation, Sendel 3.1, and the new evaluation, result is here with this excitation function. The COV value located here. It's only 5 PCM over estimation. It's not too bad.
No,
that means
the uncertainty in terms of percentage.
Yes.
Neutrons capture cross-section, which is very important for calculation, is thorium.
Yeah.
At that time, once again, it was plus or minus 20%.
Okay, maybe give the microphone to.
Oh, sorry.
There is the world expert on thorium data, Mr. Gannison.
Yeah.
I think
it's on.
Yeah, thank you. See, I understand that all your statements are relative to your evaluation center.
Exactly.
So that's very clear. So when you say it's low, according to your previous evaluation, you are revising the evaluation. So this is done every few years. You have gone to Sendel 3.1 from Sendel 1. India has not done even Indian 1. We are going into it shortly. But one small comment I want to make on the Thor assembly. You showed one graph where the Thor critical assembly was analyzed, but that is a plutonium core surrounded by a thorium blanket. So we found in one of our benchmark analysis of this same benchmark, it's a Los Alamos benchmark. It's a plutonium sphere surrounded by a thorium blanket on the left on the top. So there what happens is that the plutonium cross-sections interfere in fixing any decision on thorium. This is what I wanted to comment. So you have to be very careful. And also, when you do a benchmark analysis, there is benchmark uncertainty in the description of the benchmark. And then you have to see whether the spectrum shifts due to these uncertainties, create a confusion in getting to conclusions. Because if your spectrum is not properly calculated, then it reflects on adjusting your cross-sections to say something is better. So it could be a results of such interaction. So this is just my comment. Otherwise, you are doing very good work, and I greatly respect and appreciate your efforts in China.
Thank you, Gannison. That was a very...
Thank you.
I think this is very important comment.
I may probably add a comment. Is that recently, I mean, in the last 10 years, we have done quite a lot of effort, particularly at CERN with the NTOF facility in measuring thorium-related nuclear data. So we have also improved the uncertainty on the neutron capture measurements of thorium-232 in collaboration with GEL as well, because we have a rather wide neutron spectrum coverage at NTOF. It's based on a spallation neutron source, so we can go to a few hundred MeV neutron energies. And this has been now incorporated into the new evaluations. So I think you should also try to refer or repeat your systematic comparison with nuclear data, not only with the nuclear evaluated data libraries. So that would be probably give you some feedback as far as upgrading or updating your Chinese evaluated evaluation file.
Okay.
Thank you.
Thank you.
And yes, and you are most welcome. You are actually just anticipating the nuclear data talks, which will be given tomorrow morning. So I think there will be plenty of new measurements to fulfill your
dreams.
Not dreams, but okay. Okay, so with this, I would like to thank you, Dr. Wu, and thank the